In the centre of Brussels stands the Parlement, the European Commission's cross-shaped building. I see it every day on my way to and from work, and I can even see it now just outside the window of Euronews' Brussels office. The building is massive with a glass and steel facade, giving it a modern appearance. Personally, I find it quite iconic, though perhaps a little boring too. With its grey tones, it often blends into the cloudy Belgian sky. Yet the home of the European executive was not always like this. The building, once mostly concrete with large glass windows, underwent renovation works between the mid-1990s and early 2000s following the discovery of flaking asbestos. Asbestos is a group of natural mineral fibres that was widely used in the construction industry for its strength, heat resistance, durability, and relatively low cost. Among others, it was used to build many houses, schools, and industrial sheds. However, asbestos also had major flaws, which were underestimated for years.
Widely applied in industry for its physical and chemical properties and competitive cost, it began to be used extensively in the 1930s and increasingly up to the 1970s. Illnesses, notably cancer, brought on by asbestos fibre inhalation appear as late as 15 to 50 years after exposure. It has therefore come to be known as a silent killer, of epidemic scale, some fear, with predictions of 100,000 deaths over the next decade or so.
During the 1970s and 1980s, many people working with asbestos began developing health problems, raising concerns around the world. In 1987, the International Agency for Research on Cancer declared asbestos a human carcinogen. Exposure to it causes cancer of the lungs, larynx, ovaries, and mesothelioma, a tumour that commonly starts in the lining around the lungs. European countries began banning the production and use of the mineral. Italy introduced its ban in 1992. The UK, my home country, did the same in 1999, and the European Union followed suit in 2005. After the ban, remediation measures were introduced to reduce the hazards of existing asbestos or dispose of it in appropriate landfill facilities. New alternatives to the mineral were developed, allowing construction to continue using safer materials. We know that PFAS and asbestos are not the same. PFAS are human-made chemicals, whereas asbestos is a naturally occurring mineral in the environment. Only certain types of PFAS are classified as carcinogenic or possibly carcinogenic to humans, whereas all forms of asbestos are recognized as causing cancer. Still, asbestos and PFAS share similarities. Both were valued industrial materials, both pose health risks, and both require professional remediation to avoid or at least reduce contamination. We don't know yet if PFAS will follow the same path as asbestos and be completely banned in the European Union, but what this story shows us is that despite resistance, societies can learn to live without once common materials. Now, houses and schools can be built without asbestos, and for those born after 2000, this material is just a distant name from history. Welcome to Euronews Tech Talks, the podcast that explores the digital, technological, and scientific landscape shaping Europe. I'm your host, James Thomas. Today, we wrap up our series on PFAS, the synthetic forever chemicals that can't be broken down in the environment or the human body, with a conversational episode. We'll feature two interviews, one conducted by me with Fajer Mushtaq, co-founder and CEO of Oxyle, a PFAS destruction company based in Switzerland, and another led by our podcast producer Alice Carnevali with Miika Nikinmaa and Diana Lau from ZeroF, a project focused on alternatives to PFAS. So, grab a good cup of tea and let's get started.
Hi, I'm Fajer Mushtaq. I'm the CEO and co-founder of Oxyle.
So, what exactly is Oxyle? How and when did its journey begin?
We are a Zurich-based clean tech startup. We are a water treatment startup. To be specific, the founding mission of Oxyle was to tackle one of the world's most persistent water pollution challenges, the forever chemicals. Growing up in Delhi, spending years and every summer there and having to always rationalize how do we use water which was not available in the summer months, it always left a deep impact on me where I knew I would like to do something about this global challenge in any context, form, or shape that I can. And later, when I moved to ETH Zurich and doing my doctoral thesis in Zurich, I also saw the hidden side of Switzerland's water treatment system now, where micropollutants like pesticides and pharmaceuticals, including forever chemicals, were being discharged, untreated, or sent for incineration, like a treatment where you burn the water. So I realized it's not just an Asian problem, it's really a problem in Europe as well, the problem of water treatment. So I devoted my doctoral thesis to this topic where I developed new materials that could not just filter or just absorb these pollutants, but really destroy these chemicals and basically leave a safe water that can be discharged. Around the same time, I also met Silvan, our current CTO and co-founder, who was on a similar mission to develop solutions that can't just treat, but also monitor in real time these pollutants to empower the end users with more information to make meaningful change about the treatment systems. And that's basically what led to the start of Oxyle in 2020. So 5 years on, the journey started back then with 2 people. Now we are over 30 people today. I think we're almost going to be 40 in the next couple of months. So really excited for this growth and this journey that we are on to solve one, if not the most biggest problem I think we're facing as a society.
Can you tell us more about the technology and the processes that Oxyle uses to deal with PFAS in wastewater?
So what we realized working so closely with the customers and talking to the market is no two wastewaters are ever the same. So every customer would have their own chemistry, if you like, their list of pollutants, their flow rates, their requirements to meet the discharge limits that are geographically very local, right? And at Oxyle, our goal has always been that we need to provide the most sustainable and cost-effective solution to our customers so that they are implementing them at scale. Hence, we go with this 3-pronged approach. We will first concentrate all the PFAS into a tiny area with, let's say, our filtration technologies or our foam fractionation technologies, Oxfoam, a proprietary tech. This concentrated water, which is now full of PFAS, then gets sent to our Oxyle technology, which is a destruction unit, where we employ light and other resources to basically break the bonds of the toxic PFAS and convert them into defluorinated, safe-to-release water, basically. On top of that, Oxsignal, a third pillar of technology, provides the customers with real-time monitoring to know what's happening in the PFAS, which is extremely crucial because today, if a customer wants to know what's in their water for PFAS, they will rely on offline lab tests, which takes weeks or months to get. So you would know a couple of weeks or months later what PFAS you released months ago. That's way too late. So we are bringing this real-time data of PFAS concentration to our customers every minute with Oxsignals.
You mentioned foam fractionation there. Can you explain a bit more exactly what that is and kind of the steps involved in it?
Foam fractionation is basically up concentration technology for PFAS. So PFAS, based on their physical properties and chemical properties, they like to foam. They're foaming agents. So what that means is like if you, for example, use some dishwasher soap and you shake the water, it foams, it bubbles up, right? PFAS has very similar properties. They're like surfactants pretty much. So if you have PFAS in the water and you pump in, let's say, air into it, like air bubbles through it, PFAS will end up foaming on the top layer of the water. So all the PFAS ends up getting concentrated on a very tiny fraction on the top layer, which you can then extract and treat that water, making sure that the rest of the water, the vast, vast majority of the water is now free of PFAS and can be easily discharged. And that's how our foam fractionation works. We pump in air to fix all of the PFAS on top layer, and we extract that to destroy that and eliminate basically most of the water which has no PFAS in it. By doing so, we can treat a large volume of water in a really small footprint in a much cheaper manner. So instead of treating thousands of liters, we'll treat 1 liter, for example, because that's where all the PFAS lies. And our technology, our follow-up technology, Oxyle, the destruction technology, is built in to destroy this concentrated volume of PFAS now.
If I'm right in thinking, in January of this year, Oxyle raised 15.3 million euros in funding to kind of scale up its solution. So what exactly is so special about this company, about your company? What makes it stand out?
One of the things we do really, really well when it comes to PFAS treatment is that we don't just treat the long and medium chains that many other technologies can treat. We go after specifically for the compounds, the PFAS, that no one else can treat today. These are the short chains and ultra short chain PFAS. These are the hardest to treat. They're the smallest compounds, they're very mobile, and they always pass through any filtration, any absorption step. That's why you see so much of them in global waters today. We know that the existing technologies like absorption or filtration, they can remove the long and medium chains. They always let the short chains and ultra short chains are completely left out, untreated. And when we compare ourselves with destruction technologies, they're also unable to treat the short and the short chains well. So this is one of our key technical benefit that we provide to our customers.
But all of this is obviously a very novel and complex area. So what technical challenges or any other challenges have you or are you experiencing?
I think this is a common challenge that any deep tech startup would tell you, right? So when you go from scaling from lab to now pilot scale to full scale, it's never trivial. There's a lot of considerations you have to take into account when it comes to supply chain, but also performance. So that's always going to be a challenge. But that's exactly the kind of team we have built in who have done this before. Apart from that, there are obviously engineering challenges, which we have to make sure that the efficacy and the cost effectiveness of a treatment is maintained at scale and can be modularized. There are a couple of challenges that are very unique to deep tech water startups, so we're not facing anything unusual there. But at the same time, I think it's apart from these technical challenges, I think we also have to be mindful that there are not a lot of water tech startups out there who are fundraising. It's very, very hard to raise funds for water. So that's something I would always say that, within the clean tech segment, water gets 1% of overall funding for all clean tech, which is way, way too low considering how big a role water plays in global warming, in human, evolution and moving around, and just efficacy of us just living healthy lives. We need more funding, we need more visibility in water. That's a challenge we've also faced when we are fundraising. But luckily for us, we have trusted partners who understand the long-term vision behind investing in a clean tech startup, which is water-focused. So we were lucky in that regard, but others are not so lucky, I would say, when I talk to my friends who are in a similar journey.
Where is your technology currently being used? Where can we see it?
So our technology as a whole is really best suited for, let's say, industrial and groundwater applications where you have presence of PFAS in a broad spectrum. So this would be applications, let's say, in chemical, agrochemical sectors, pharmaceutical, plastics, and even construction companies today. And we'll be going on site the next couple of months with applications here in Switzerland, but also in Belgium and Netherlands. So these are all applications around chemical construction agencies where it's prime target for us.
And what does the future hold for the company? It seems like you've made a lot of tremendous strides already, but what's next? What's next on the horizon?
Our goal is to really grow a team so we can handle multiple projects all over across Europe with our team and go to different segments. And hopefully in the next 3 to 4 years, go out with a big round, which will be around our expansion into US market after that as well. So you want to make sure that in 3+ years, we are going into the American market, which again, has a lot of PFAS issues and is an underserved market. So it's all around growth, going beyond geographical locations, but also going beyond our existing customer base of chemical, agrochemical into more nuanced fields that we know we can make a big impact as well. And all this happens with more funding and with a bigger team. So all exciting milestones we're looking forward to.
You've just listened to my conversation with Fajer Mushtaq, CEO and co-founder of Oxyle. Her startup has developed 3 complementary technologies to tackle even the most persistent PFAS contaminants in wastewater. The process begins with Oxfoam, a system that uses foam fractionation to separate PFAS from large volumes of water. Next comes Oxylite, a treatment that breaks the carbon-fluorine bonds in PFAS molecules using light. Finally, Oxsignal provides continuous monitoring of PFAS levels and treatment performance. These are methods to collect and destroy PFAS, but where do we stand when it comes to finding alternatives? Alice Carnevali explored this question with people involved in the European project ZeroF.
My name is Diana Lau. I'm working at Fraunhofer ISC Institute for Silicate Research in Würzburg. And within the ZeroF project, I'm a work package 2 leader dealing with the synthesis of the coating building blocks.
My name is Nikinmaa. I'm a lead in biomaterial solution at VTT Finland. And in ZeroF, I'm a project coordinator.
Miika, since you're the project coordinator of ZeroF, can you tell us more about ZeroF, what it is and what its aim is?
ZeroF is a Horizon EU project, and we are aiming to eliminate per- and polyfluoroalkyl substances from packaging and textile applications. While we are doing this, we are implementing the Safe and Sustainable by Design framework by the Joint Research Council and developing computational tools to aid us in this work. The project is funded by European Union and ZeroF from Switzerland, and we are 12 partners from 9 different countries.
And Miika, let me turn back to you. What solution has ZeroF created for now to replace PFAS when it comes to food packaging?
The packaging side, we are working to replace single-use food service items that are typically made from plastic with the molded pot trays and cups. In ZeroF, we are starting from very, very fundamental building blocks. So starting from the synthesis of these chemistries, and then we go all the way to application. So throughout the whole value chain in a single project. If we go to packaging value chain, then we are working on this modified celluloses, so cellulose derivatives, and more precisely cellulose fatty acid esters.
So as an alternative to these forever chemicals, so these man-made substances in food packaging, you're developing cellulose. Can you explain what that means? What is cellulose?
Cellulose is the most abundant polymer in the earth. So you can find it in the single-year crops, but most often it's available from different kind of trees processed by pulping industry. That's the most abundant source commercially. But of course, cellulose can be obtained from nearly any plant or basically any plant in the nature. And we take cellulose and we craft these fatty acid chains with different chain lengths on the backbone. And this is done to increase the water and oil resistance, but also to change the nature of cellulose to be thermoplastic so that we can process it easier when it goes through. And then once you have the chemical, then we need to ensure that we can transfer it to substrates that can be applied on surfaces. And this is, of course, very, very challenging. And depending on the chemistries you're using in this packaging value chain, we decided to apply different methods. So throughout this testing, we achieved good performance. So in laboratory, we were able to meet the requirements that we set for ourselves in this grant agreement. And that was based on the industry's demand.
Now, Diana, let's go back to you. Can you tell us more about the other part of this project, meaning what are the alternatives that you are trying to find to substitute PFAS in upholstery textile?
We develop new fluorine-free coatings based on our Ormosair technology. Ormosair is a trademark of the Fraunhofer Gesellschaft, and Ormosair stands for organically modified ceramic. So this is an inorganic-organic hybrid coating material, and it's based on the salt gel reaction of silanes and siloxane precursors. And here you can vary these precursors and change the inorganic and organic parts. So the idea is to take properties of inorganic materials and to combine them with typical properties of organic materials. And by varying these precursors, we can really modify the properties of the coating materials. And by doing so, we can address several characteristics which are typically common for PFAS materials, such as, for instance, the chemical stability, high temperature stability, and also the repellency against water and dirt. And these coatings, they are especially promising in various industrial applications because they have excellent processing properties and surface and barrier properties. And within the ZeroF project, we have additionally incorporated these cellulose-based fatty acid esters, which Miika already mentioned and which were prepared by VTT.
What are the technical challenges that you've faced, Diana?
One challenge which has to be mentioned is, of course, the performance. So it's quite a big challenge, or the major challenge, to develop PFAS-free coatings with really a comparable performance, especially in terms of oil and water repellency. So to address one of the mentioned characteristics, so meaning either the water or the oil repellency, this is not that difficult. But we would like to address both together. And this is really a tricky part because the great water and oil repellency of PFAS is related to the nature of the carbon-fluorine bond. And since it is quite short and quite strong, it can nearly not be affected by any chemical attack. So to get coatings with a similar performance, we cannot only simply change a single atom. Instead, we really need to combine completely new chemical building blocks, have to design them, and also work with patterning of created surfaces to address similar low surface energies and therefore comparable performance.
Performance is one of the biggest challenges. I suppose that the other big challenge is economic, Miika. Chemical companies often argue against a total PFAS ban by claiming that PFAS are essential to keep some products affordable, while alternatives would drive up prices. Is that a risk that your alternatives could face? And if yes, how are you addressing it?
The cost of product and cost of production is very company specific. There are companies who have a wet process, and replacing PFAS in that system would be nearly impossible, and you have to do a significant investment. But then there are also companies who are working towards this kind of technology, have addressed it, and do have processes such as coating systems in place, and they can kind of meet the demands with, I would say, more affordable cost than you would assume in this point. But I would say that in addition to PFAS, we have to bring other properties. We have to be recyclable, and we have to meet the new demand.
That's quite of an important point, like not just replacing PFAS and meet the performance, but also give to the consumer something even better.
Exactly. So it will be the markets to decide what is the cost. And talking to these molded producers, I have to say that these people are very enthusiastic and its community is very vibrant. So I'm expecting good things coming from the ZeroF group, but also the external stakeholders who are working towards this goal of replacing fluoropolymers on the market.
Diana, what are, according to you, the benefits, the strength that your alternative have as compared to PFAS?
Our solution will not be able to completely replace PFAS because, as Miika mentioned, there will not be only one single solution to replace PFAS. It's a broad class of materials with really many properties associated with a wide range of applications. But with our alternative, with the almost same materials, we can address several properties which are typical for PFAS materials. So chemical resistance, water repellency, to a certain level, the oil repellency. And with this tool in hand, we can also address other applications where PFAS are commonly used. And this is the great advantage.
And Miika, where are we at with your project now?
The ZeroF is a 3-year project, and we are reaching to the end now. And as I said, that this was research and innovation action. So the kind of follow-up from this would be that there will be a innovation action and then the flagship project according to EU kind of funding scheme. But then, of course, some of the activities might move much faster. And of course, Young is just announced that they secured additional funding and their process is going forward very quickly. And of course, then I'm very excited about this new cellulose derivatives that we are developing. But of course, those will require some time before they become commercial.
That was Miika Nikinmaa and Diana Lau from ZeroF, the project trying to find alternatives to PFAS. And this brings us to the end of our episode and of our journey into the world of PFAS. We hope we've given you the necessary tools to navigate this complex scientific topic, and we thank you for following us thus far. We had hoped to include an additional episode featuring a debate between groups supporting and opposing an EU-wide PFAS ban. As things stand, associations against the ban have declined to participate, but our invitation remains open. We'll be back in 2 weeks, this time diving into the topic of energy and space. I'm your host, James Thomas. This series was created by Marta Rodriguez Martinez. This episode was written and produced by Alice Carnevali. The theme music is by Leo Lebrun. Sound editing and sound mixing is by Joanne Breton. Our editor-in-chief is Niaz Samadizada. If you aren't already, you can listen to this series on Apple Podcasts, Spotify, Castbox, or wherever you get your podcasts. Find us also on Euronews' YouTube channel. If you're enjoying the podcast, please consider leaving us a positive review and, of course, sharing it. Thanks for listening.